All of you, I'm sure, are familiar with what chemical reactions are. And a really good analogy to this is to think about cooking. When you cook, you start with the initial reactants. So those are the substances entering the reaction. Then once you do the cooking, once you maybe heat it up on the stove, once you put the ingredients together, so those reactants could be thought of as ingredients. Once you do the cooking and put the ingredients together, you then come out with the products. That's the result. So a chemical reaction is represented by a chemical equation. We're not going to be balancing any chemical equations or anything like that. Like I mentioned at the beginning of this chapter, it's very basic chemistry and the chemistry that pertains to the body. So compounds are represented as molecular formulas. So water is H2O. I think you all know that. Glucose is C6H12O6. Hydrogen is represented as H2, and methane is CH4, which we saw on the last video. The subscript indicates the number of atoms, and the prefix is going to indicate the unjoined atoms or molecules. So in this case, there are two atoms of hydrogen that combine to make hydrogen gas. And the arrow represents the direction of the chemical reaction. Here we have four atoms of hydrogen, one atom of carbon combining to make methane gas, CH4. So the reason this is important in the body is because we have three main types of chemical reactions to know. The first one is synthesis. This is taking smaller molecules and putting them together to make larger molecules. And this can be done for all of the macromolecules that we'll be talking about later in the semester. So things like proteins, carbohydrates, nucleic acids, or lipids. In this case, we have small monomers called amino acids. And a monomer means it's an individual unit or the building block of one of these larger macromolecules. So macro means that it is made up of many individual monomers. So amino acids are put together to make proteins. The opposite of that would be a decomposition reaction. And we could simply turn the arrow here in this direction, and that would be a decomposition reaction. However, the example that they give you is using starting with a macromolecule and breaking it down into a monomer. So the glycogen would be a macromolecule. It's actually a macromolecule that's stored in your skeletal muscle and also in your liver. So whenever your body needs glucose released out into the blood plasma, glycogen is broken down into these smaller pieces and parts called monomers, and it would be a decomposition reaction. But we could easily reverse this, and it would be a synthesis reaction. So in the body, chemical reactions go in both directions based on whatever the need at that point in time is. The third type of chemical reaction you need to know is an exchange reaction. I always like to think of this as if there's a couple that goes on to the prom and there's someone that goes stag. We used to call it stag back in my day, but they go by themselves. So at the prom, what happens is the person that was by themselves then ends up dancing with the date of somebody else. That would be an exchange, if you will. And in the body, it's also called a displacement reaction. But what happens here is there's a large macromolecule called ATP, adenosine triphosphate, which is going to combine with glucose. So imagine the ATP came by itself to the prom. And or this is the couple that came to the prom. Sorry, ATP is the couple. And one person one part of that couple, this P here, is going to then dance with the person that came by themselves. That happens to be glucose. So the phosphate combines with the glucose to make a new molecule, glucose phosphate, it's called. So it's an exchange reaction. And think of that analogy as the prom. So essentially, there's two things, people that are dating, there's one by themselves, and one of those people combines with the glucose. This chemical symbol formula, you're not going to have to recognize any of those, anything like that. But you should know that ATP plus glucose is an exchange reaction. And that's important because what's left over is now called ADP, and the D means diphosphate. It's got two pieces of phosphates in it. Now, when these reactions happen, and there's really two examples of what can happen. Either energy is going to be released. So if it gives off energy, that's what's called an exergonic reaction. Look at the beginning of the word. It kind of looks like exit, and the products have less potential energy than the reactant. And it's a catabolic and oxidative reaction. Catabolic means that large molecules are broken down into small molecules. So this would be our example of the exergonic reaction. So again, it would be catabolism, which means large molecules are broken down into small molecules. So one example of this would be proteins could be broken down into amino acids that would release energy. The opposite of that is going to absorb energy or use up energy, and that's called an endergonic reaction. And that would include anabolic reactions, which is the opposite. Both of these are types of metabolism, but in anabolism, small molecules are put together to make large molecules. So we could have amino acids added together to make proteins. But in order for that to happen, that's going to require energy. So in the body, as I mentioned, these chemical reactions can go either way, basically, depending on the needs of the body. So they are theoretically reversible. So we really represent them with a double-sided arrow. And again, the reaction is going to go one way or the other, depending on what the need is for homeostasis. So energy requirements to go backwards, sometimes too high, but the speed of the reaction is affected by what's called an enzyme. And it's very important that you know various characteristics of an enzyme. They are called catalysts, which increase the rate of the reaction without being chemically changed. The speed of the reaction can be changed by things like increasing the temperature, the concentration of the reactants, and the particle size. But in the human body, we don't really, I mean, you can't just turn up the temperature. Your body temperature could increase a little bit. But if you think about a campfire, if you're making a campfire, you're going to want to cut the wood into smaller and smaller pieces to increase the surface area. That's why it would produce smaller and smaller particles, which increase the rate. But in the human body, we have these enzymes. And we're going to talk about more about enzymes when we get to the protein section of this chapter a little bit later on.